But yeah, I wanna pick up where we left off, which is doing these Apollonian circle constructions. And we did, what did we do? We did, so that was LLP last time. Now I wanna go LPP, or PPL, or whatever order I listed this in. Which means we're given a line and 2 points. We want to construct the circle tangent to all 3 of them. So tangent to the line and passing through the points. So construct a circle through 2 given points. And tangent to a given line. Turns out this has a fairly easy solution once we establish we can construct geometric means. And geometric means, we'll see, are not just useful for proving this problem. When we come up to the constructability of particular numbers, it's really interesting to observe this. So first, we're going to take a detour to geometric means. Do you guys know what a geometric mean is? You know what an arithmetic mean is, right? Arithmetic mean is just an average. So if you have n numbers, the arithmetic mean is the average of them. Geometric mean is, instead of adding them all, you take the product and you take the nth root. So geometric mean is the product raised to the 1 over n. So we're not doing that in full generality. Geometric mean, we're just going to have 2 numbers here. Some people call this the mean proportional. The textbook does in particular. I hate this expression. Hate's a strong word, but I call it the geometric mean. So the geometric mean, or mean proportional z, of 2 quantities. Let's call them x and y. Is given by z is the square root of x times y. Right, in this case I just have 2 numbers, so it's the product of them raised to the 1/2 power, the square root. And what I want to prove is that if I have any 2 lengths, so if I have a segment of length x and a segment of length y, I can always construct a line segment whose length is the geometric mean of both of them. So square root of x times y. So here's our problem. Construct a length equal to the geometric mean of 2 given lengths. All right. Can I erase this? So here's our solution. So what I have is I have two lengths, right? I've got, I'm given one length, say AB, and I'm given another length, say CD. First thing I want to do is I want to observe that I can draw these end to end. So I have these two lengths. One is of a length AB, one is of length CD. I don't have to assume they're given like this. I can actually always assume that these are given in a straight line. So now I really have two lengths, AB and BC. Why can I always assume they're given in a straight line? Well, I can just use my compass memory, right? If BC is actually down here, then it doesn't make sense to call both of these points B. But if I have some other length, I can just set my compass to this length, come up to AB, put the pokey end on B, and draw a circle of that radius, right? And then just extend this line out to C. So I can always assume that they're just given in a straight line. And if they're not, reposition them so that they are, like so. So one is using the memory of our compass we can assume the lengths are AB and BC arranged in a straight line. A straight line as shown. All right, what now? Now I'm going to construct the midpoint of this segment, AC. So we'll construct the midpoint. I'm not actually going to label it because I don't think I care about the midpoint in particular. But once I've constructed the midpoint, now I can construct the circle passing through A and C. And again, I'm only going to draw the portion that I really care about, which is just a semicircle. So here's half of it. So step 2, construct the midpoint M of AC and draw the circle centered at M. So maybe I will label just for the picture. Construct this, or the circle centered at M passing through A or C. And draw a circle centered at M and passing through A and C. All right, last but not least, this is really all you need to do. Come into B and erect a perpendicular. And the point where it meets the circle, we'll call that point P. Erect a perpendicular from point B and let P be the point where it meets the circle. My claim is that this is what we wanted. The length of BP is the geometric mean of AB and BC. So for BP is the square root of AB times BC. So we have found, let me not say found, we have constructed the geometric mean. Why? Well, we need to prove this, but there's the construction. So we've gone through with just a straight edge and a compass, and we found, starting with two lengths, we found another length equal to the square root of their product, which is kind of impressive, right? A big deal in constructions is this question of what numbers can we construct. And now I know I can construct square roots of other numbers that we can find, but we'll talk about that at a later date. I shouldn't have raised this picture. I want to prove the statement. I'm going to use the picture to do it, so let me just reconstruct that. So proof, and we had A, C, V, P. That's a right angle. My first claim is that these two triangles are similar. Why are they similar? Well, it's just an AA argument. Clearly they both have right angles, so that's good. Angle ABP is equal to 90 degrees, which is the same as the measure of angle PBC. Let's call it CBP. So they both agree here on this angle. And what I'd like to claim is that this angle and this angle are the same as well. Why is that? Well, what's this angle equal to? This angle would be equal to 180 minus 90 minus this angle, right? So, and angle BAP is exactly what we just said, 180 minus 90, so just 90. 90 minus this angle, 90 minus BPA. But what is 90? Well, this is actually, that angle here, that angle is 90 degrees. How do I know that's right angle?
AC is the diameter.
Yeah, AC is a diameter, so that's a right angle. So 90, I'm just going to replace this with APC, angle APC minus minus BPA. And angle APC minus BPA is just this angle here, right? Take the whole angle, subtract off this piece, and I'm left with this piece. So that's equal to angle BPC. So by AA, we have a similarity of triangles. Let's call it ABP, that's what I'll call the first triangle. So this triangle here is similar to this one, and I've got to make sure my points match up. This angle is corresponding to this angle, so A goes to P. This is similar to P this angle goes to this angle, so next up we've got B corresponding to B. Think of this similarity as just, I pick up this guy, I rotate it, so that this angle goes up here, this stays fixed, and I shrink it down a little bit so that this angle goes here. So P, B, C. Why does this help? Well, similar triangles have sides that are in sort of proportion to each other. So the big triangle, let's see, AB. AB over this side here. When I pick it up and rotate it, this side here goes to this side here. All right, so AB over BP is the ratio of corresponding sides. This guy corresponding to this guy is in the same proportion as, so now I'm starting with this side. I'm starting with this side of the original triangle. BP over, in my similarity, this side in the first triangle, where does it go? Well, again, think of picking it up and holding this point fixed and just rotating it. This side goes down here. So that would be BP over BC. The other way you could do this algebraically without having to look at the picture is just BP corresponds to BC. What does that mean? Cross multiply. That means BP squared is AB times BC. And then we're done, right? That's exactly what we wanted to show. It's the geometric mean. So BP is the square root of AB times BC. So geometric means are always constructible. And not a difficult construction either. You literally just have to place your two lengths end to end, collinearly, and raise this perpendicular up to the circle. Okay, so we can come back now to our original problem, this Apollonian circle construction, or circle problem. And again, this is solution to, which one we're doing, LP, PPL? Maybe I called it LPP. I'll stick with the same word. In any case, I have a line and 2 points. So let's see. Let's give these things names. Let P and Q be the given points. Let P and Q be the given points, and AB the given line. So there's actually two cases here. I think the text only proves one case. Let's do both of them. We have time. Case one is if you draw the line through P and Q, so here's P, Q, let's go P, Q, this way. And I've got my given line, AB. Case one is the line PQ actually intersects AB, so they're not parallel. So case one is PQ not parallel to AB. So first thing we're gonna do is just draw what I have already, but we're gonna extend this. So we're gonna draw a line PQ and let U be the point of intersection. So step one, draw a line PQ and let U be the point where it meets AB. So what's my circle gonna look like here? Well, I want it to pass through both these points and be tangent to this line. So my circle has to look something like, probably something like this, right? And I actually know something about this point here. I know exactly how far away that point has to be from U. So what we're gonna do is we're gonna construct, and we'll prove this after, we'll prove why this has to be exactly this distance from U, but we're gonna construct a V on this line a certain distance away from U. So 2 is, since we can construct geometric means, construct V as shown so that the distance U is from V is the geometric mean of UP and UQ. All right, so there's a lot going into this. I want to point out a few things here. So I have these two lengths. I have UP and UQ. I can take those two lengths and I can construct the geometric mean of them. Right, that's something we just demonstrated. Given two lengths, UP and UQ, I can find the geometric mean. Then I can take that distance, I can take that length, the geometric mean, I can use the memory of my compass once I've established whatever length that is, and I can draw a circle through U set to that compass distance to construct V, this given distance away from U. And I'm being a little bit lazy here, so I'm relying on my picture. I'm saying construct V as shown because I haven't written down all the details. If I didn't have a picture, I'd have to say construct V on this line AB on the same side as of U as QP is. Somehow I'd have to be precise about that. But with the picture, this is exactly where I want to put V. And my claim is that this is the circle. So now all I have to do to get the circle is construct the circumcircle of this triangle. So I'm not even going to draw on the triangle, I'm just going to say construct the circumcircle. Construct the circumcircle of triangle PQV. This circle obviously passes through all 3 points. This circle passes through P and Q, obviously, by definition of being a circumcircle. And it's tangent to AB at V. So clearly, and is tangent to AB at V. That last part needs proof. How do I know it must be tangent here? So we need to prove that. Let me make a note of this. UB is the square root of UP This goes way back to chapter 1. End of chapter 1, we had a theorem. Use theorem, I believe it's 1.35. Let me check my notes on that. Yeah, it's 1.35. What did theorem 1.35 say? This was the thing about if I have two chords passing through a circle from an exterior point, and I believe we call this P, let's call it X, Y, U, V. If we were in this situation, this was the theorem saying that the products of these distances doesn't actually depend on P. No, it does depend on P. It doesn't depend on the lines you choose. The only thing it depends on is P, right? So this told us that Px times Py, these chords intersect at 2 points, P, X and Y. So if I take the product of these distances, Px times Py, that's exactly the same as Pu times Pv. You remember this theorem? That's what I'm going to use here. So let's say suppose the circumcircle meets AB. If it's passing through V, then it meets the circle, or it meets the line at least one point. It meets the line at least one point on AB at B. At most, it meets it at another point, W. Right, so we'll say suppose it meets AB at 2 points, V and W. Right, then by theorem 1.35, we have that UV times UW. So it's passing through a circle at these 2 points, V and W. So UV times VW should be UQ times UP. But I already know what's UV times UV. If UV is the square root of UP times UQ, then UV times UV is just UP times UQ. Right, so that's UQ times UP. Change the order here, because for whatever reason I wrote it as UQ times UP, but UV times UV is UP times UQ. And that's by definition, by our construction of this particular length. What does that mean? Well, that means that UV times UV is equal to UV times UW. That means, cancel out one of those, that means UV and UW are the same length. If these two distances are the same length, then they actually are the same point, right? So this means V is equal to W. And that means our circumcircle doesn't meet AB at 2 points. It can't. If it meets it at another point, that point must be the same as V. So it actually is just tangent to AB at the single point V. Notice I'm just using a bunch of arrows because I don't want to write all these words. In a formal proof, you'd probably make it look a bit better with some words, but this implies that the circumcircle is tangent to V. So we still have 15 minutes, a bit less time than I expected to have when we get to this point, but why don't you try this one? So the book doesn't go through this. Try case 2. Assume they're both parallel. So case 2 is PQ is actually parallel to AB. Again, you know what your circle is going to look like. Something like this. And once again, what you're really just trying to find is that point there. And the previous, the construction we just did doesn't really help at all. This one's going to have to look completely different. What's your plan, James?
Is it just the perpendicular from the midpoint of PQ?
Yeah, so I believe all you have to do is construct the perpendicular bisector.
Yeah.
Right, come into here and drop this perpendicular bisector. Because these are parallel, if that's a right angle, this must be a right angle. And yeah, I think that does it, right? This is perpendicular bisectors from chords always pass through the midpoint of the circumcircle, not the midpoint, the center of the circumcircle. So yeah, I believe all you have to do is construct the perpendicular bisector that meets AB at this point V, and then construct the circumcircle. So 1, construct the perpendicular bisector of PQ. 2, let V be the point where it meets AB. And 3 is draw the circumcircle. Draw the circumcircle of triangle A, not A, B, P, Q, V. By the way, you might find it odd that I've been labeling P on the right of Q. It feels more natural to go P, Q, but I'm doing that just so when I order my vertices counterclockwise, that they're in alphabetical order. But yeah, and that must be tangent, because we know that by construction, this must be a right angle right here. And it passes through a perpendicular drawn from B passes through the center of the circle. So this is by definition, AB is a tangent at B. That's all you have to do. So yeah, if this class had gone extremely quickly, I'd planned to talk a little bit about, jump straight to 6E and talk a little bit about constructible numbers. But I'll probably, I'll postpone that till maybe the end of next week. So next week we'll do 6D, a couple of hard problems that were of interest to these ancient Greek geometers, mathematicians with these constructions. And then I think we'll end on Friday next week with 6E. So this question of constructible numbers and the observation that proving that certain numbers aren't constructible, certain lengths. So for example, if I just take a length, I can call that length 1. Now I can construct lengths of 2, 3, 4, all the integers. We can actually construct all rational numbers. And with geometric means show we can construct square roots. But there's certain numbers that aren't constructible, like pi. And when you show that certain numbers aren't constructible, then you prove that some of these ancient questions about can I square a circle or can I trisect an angle, these constructions just aren't possible. And this took almost 2,000 years to resolve, but yeah. It turns out that certain constructions, proving you can't do them, requires modern day algebra. So anyway, see you guys next week. Oh, by the way, I'll post up the homework. I'll try to get it posted tonight to give you a little bit of extra time. Again, it's completely optional. It's sort of extra credit. I'm just going to use this homework, if you do it, to replace your previous lowest homework score. So. And the way I'll do that in the gradebook is I'm just going to tell it to drop 1. So if you didn't do this homework, that drop 1 would apply to this homework. Mathematically equivalent.